Welcome to Fuzzy Mathematics, the basics. In the previous lecture, we have talked about the representation theorem. In this lecture, we will continue this topic. First, let's recall the representation theorem. Let T be a mapping from the set of the nests of sets to the fuzzy power set. The fuzzy set T of H is the union of the scalar multiplication of lambda and h of lambda. Then T is a surjection and a homomorphic mapping, and the following properties hold. Firstly, h of lambda is in between the strong cut and cut of the fuzzy set T of H at level lambda for all lambda in the closed interval from 0 to 1. Secondly, if lambda is in the interval from 0 to 1 excluding 0, then the cut of T of H at level lambda equals the intersection of h of alpha, alpha less than lambda. Thirdly, if lambda is in the interval from 0 to 1 excluding 1, then the strong cut of T of H at level lambda equals the union of h of alpha, alpha greater than lambda. That's the representation theorem. If lambda equals 0, what is the cut of the fuzzy set T of H? The cut of T of H at level 0 is the universal set. If lambda equals 1, what is the strong cut of the fuzzy set T of H? The strong cut of T of H at level 1 is the empty set. The representation theorem provides an approach to construct a fuzzy set by a nest of sets. Now let's look at corollary 1. Let H be a nest of sets in X. Define T of H is the union of the scalar multiplication of lambda and h of lambda. Then T of H is a fuzzy set, and the degree of membership of X in the fuzzy set T of H is the supremum of lambda, such that X is in h of lambda. By the representation theorem, we have that h of lambda is in between the strong cut and cut of T of H at level lambda for all lambda in the closed interval from 0 to 1. By the corollary of the resolution principle 3, T of H of X is the supremum of lambda such that X is in h of lambda. This completes the proof. We have known that T of H is the union of the scalar multiplication of lambda and h of lambda. Here the union is taken over all lambda in the closed interval from 0 to 1. Divide the closed interval from 0 to 1 into two parts, 0 and the interval from 0 to 1 excluding 0. By the associativity of the union of fuzzy sets, the union equals the union of the two unions. It is easy to see that if lambda equals 0, then the scalar multiplication of lambda and h of lambda is the empty set. So the fuzzy set T of H equals the union of the scalar multiplication of lambda and h of lambda. Lambda is in the closed interval from 0 to 1, excluding 0. Let's do some examples. First, example 1. Let X be the set of x1, x2, x3, x4, x5. Let H be a nest of sets. If lambda is greater than or equal to 0 and less than 0.3, then h of lambda is the set x1, x2, x3, and x4. If lambda is greater than or equal to 0.3 and less than 0.6, then h of lambda is the set of x2, x3, and x4. If lambda is greater than or equal to 0.6 and less than 0.9, then h of lambda is the set of x3 and x4. If lambda is greater than or equal to 0.9 and less than or equal to 1, then h of lambda is the empty set. Define A is the union of the scalar multiplication of lambda and h of lambda. Find the fuzzy set A and denote it by Jedi notation. By the corollary of the representation theorem, the degree of membership of x1 in A is the supremum of lambda, such that x1 is in h of lambda. Element x1 is in h of lambda if 0 is less than or equal to lambda, less than 0.3. But x1 is not in h of lambda if lambda is greater than or equal to 0.3. the supremum is 0.3. Similarly, using the same formula, replacing x1 by x2, we have the degree of membership of x2 in A is the supremum of lambda such that x2 is in H of lambda. Element x2 is in H of lambda if 0 is less than or equal to lambda, less than 0.6. But x2 is not in H of lambda if lambda is greater than or equal to 0.6. The supremum is 0.6. The degree of membership of x3 in A is the supremum of lambda, such that x3 is in H of lambda. Element x3 is in H of lambda, less than 0.9. But x3 is not in H of lambda if lambda is greater than or equal to 0.9. The supremum is 0.9. The degree of membership of x4 in A is the supremum of lambda, such that x4 is in H of lambda. Element x4 is in H of lambda if 0 is less than or equal to lambda, less than 0.9. But x4 is not in H of lambda if lambda is greater than or equal to 0.9. The supremum is 0.9. The degree of membership of x5 in A is the supremum of lambda, such that x5 is in H of lambda. Element x5 is not in any H of lambda. The supremum of the empty set is 0. Finally, we denote the fuzzy set A with Jedi notation. A equals 0.3 over x1 plus 0.6 over x2 plus 0.9 over x3 plus 0.9 over x4 plus 0 over x5. And the degree of membership of x5 is 0, so the last term can be omitted. Another example, example 2. Let H be a nest of sets in the set of real numbers. Suppose H of lambda is the closed interval from lambda minus 1 to 2 minus lambda. Lambda is in the open interval from 0 to 1. Define A is the union of the scalar multiplication of lambda and H of lambda. Find the membership function of A. By the representation theorem, we have A is a fuzzy set in the set of real numbers R. It would be a little difficult to solve the problem directly, but we will try to find the kernel of A and the support of A. First, let's find the kernel of A. That is cut of A at level 1. By the representation theorem, if lambda is in the interval from 0 to 1, excluding 0, then A sub lambda is the intersection of H of alpha, alpha less than lambda. So, if lambda equals 1, then the cut of A at level 1, that is the kernel of A, is the intersection of H of alpha, alpha less than 1. Because H of alpha is the closed interval from alpha minus 1 to 2 minus alpha, it is easy to see that the greater the alpha, the smaller the interval. As alpha goes to 1, alpha minus 1 goes to 0, and 2 minus alpha goes to 1. The intersection is the closed interval from 0 to 1, including 0 and 1. Therefore, A of x equals 1 if and only if x is in the kernel of A, if and only if x is in the closed interval from 0 to 1. Next, let's find the support of A, that is the strong cut of A at level 0. Again, by the representation theorem, if lambda is in the interval from 0 to 1, excluding 1, then the strong cut of A at level lambda is the union of H of alpha, alpha greater than lambda. So if lambda equals 0, then the strong cut of A at level 0 is the union of H of alpha, alpha greater than 0. Again, because H of alpha is the closed interval from alpha minus 1 to 2 minus alpha, it is easy to see that the less the alpha, the greater the interval. As alpha goes to 0, alpha minus 1 goes to negative 1, and 2 minus alpha goes to 2. As alpha goes to 0, the interval expands to the open interval from -1 to +2. The support of A is this open interval. Therefore, A of x is greater than 0 if and only if x is in the support of A, if and only if x is in the open interval from -1 to +2. That means A of x equals 0 if and only if x is not in this open interval. And we have known that A of x equals 1 if and only if x is in the closed interval from 0 to 1. What else? Now we can find the degree of membership of x in the fuzzy set A. By the corollary of the representation theorem, the degree of membership of x in A is the supremum of lambda, such that x is in H of lambda, which is the closed interval from lambda -1 to 2 minus lambda. That is, A of x is the supremum of lambda, such that x is greater than lambda minus 1, and x is less than or equal to 2 minus lambda. Here x is greater than lambda minus 1. That is, lambda is less than or equal to 1 plus x. X is less than or equal to 2 minus lambda. That is, lambda is less than or equal to 2 minus x. So, the supremum is taken over lambda. Lambda is less than or equal to 1 plus x, and lambda is less than or equal to 2 minus x. If x is in the open interval from -1 to 0, then the supremum is 1 plus x. And if x is in the open interval from +1 to +2, then the supremum is 2 minus x. Therefore, the membership function of A is as follows. By the way, I'd like to mention that when you meet questions similar to example 2, you may try to find the kernel or the support of A first. That's the end of this lecture. Next time, we will move on to a new topic, the extension principles. Thank you.